In 1907, a young patent clerk sat at his desk in Bern, Switzerland, and had what he would later call the happiest thought of his life. He imagined a man falling freely from the roof of a house. For that man, Albert Einstein realized, there would be no sensation of weight at all. He would not feel himself falling. He would feel nothing pulling him downward whatsoever. And from that single, almost absurdly simple image, an idea began to take shape that would eventually dismantle 200 years of physics. Because if a falling man feels no gravity, then maybe gravity itself is not a force reaching out and grabbing him. Maybe it is something else entirely, something stranger. Something that had been hiding in plain sight since the moment Isaac Newton first wrote down the law that every physics student still memorizes today. For over 3 centuries, we have told a very simple story about why things fall. Mass creates gravity. Gravity pulls objects toward each other. The heavier the object, the stronger the pull. It is intuitive, it is elegant, and it works well enough to send rockets to the moon. But here is the uncomfortable truth this video is going to lay out, piece by piece, using verified physics, real experiments, and the works of the scientists who actually did the work. That story is not correct. Mass does not create gravity in the way we picture it. There is no invisible rope stretching between the earth and the apple that falls from the tree. What is actually happening is something so different from our intuition that when Einstein first proposed it, even some of the greatest minds in physics dismissed it as unnecessary mathematical decoration. They were wrong. And by the end of this investigation, you will understand exactly why and exactly what mass is actually doing to the universe around it. Before we go further, let's be clear about what kind of investigation this is. We are not here to entertain a fringe theory or chase a sensational rumor. Everything in this video is drawn from peer-reviewed physics, confirmed by repeated experimental tests over more than a century, and supported by the direct observational evidence of institutions like NASA, the European Space Agency, and the LIGO scientific collaboration. What we are doing is something different from the way this topic is usually explained. We are going to trace the actual chain of reasoning, the actual evidence, and the actual scientific debate that took gravity from a mysterious force acting at a distance to something Einstein described not as a pull, but as a shape. Let's start with Isaac Newton, because to understand why his idea was replaced, we first have to understand how good it actually was. In 1687, Newton published the Philosophiae Naturalis Principia Mathematica, laying out his law of universal gravitation. The idea was that every object with mass exerts an attractive force on every other object with mass, and that force depends on how much mass each object has and how far apart they are. Newton's equation could predict the orbits of planets with stunning accuracy. It could explain why the moon circles the Earth and why an apple falls from a tree, using the exact same underlying rule. For the first time in human history, the heavens and the Earth were governed by one unified law. This was revolutionary. It is one of the greatest achievements in the history of science, and it still works remarkably well for almost every calculation we do in daily life, from launching satellites to calculating the trajectory of a baseball. But Newton himself was deeply uncomfortable with his own theory, and this discomfort is a detail that rarely makes it into popular science content. In a letter to the theologian Richard Bentley in 1692, Newton wrote that the idea of one body acting on another through a vacuum, without anything in between, was to him so great an absurdity that he believed no person with a competent understanding of philosophical matters could ever accept it. Newton described gravity's mechanism as something he could not explain and did not pretend to know. He gave the world a formula that predicted gravity's effects with extraordinary precision, but he openly admitted he had no idea what gravity actually was, or how it managed to reach across empty space instantaneously and pull on distant objects. For over 200 years, physicists used Newton's law anyway because it worked. But the question of what gravity actually is remained an open wound in physics, waiting for someone to reopen it. That someone was Einstein, and the reopening began with that falling man in 1907. Einstein called it the happiest thought of his life, because it revealed something that Newton's framework could never explain. If you are in free fall, you feel weightless. This is the exact same sensation astronauts feel orbiting the Earth. They are not, as many people assume, floating because they have escaped Earth's gravity. They are still very much within its grip, falling continuously toward the Earth, but moving forward fast enough that they continuously miss it. This constant falling produces weightlessness. And Einstein realized something profound in this. If being in a gravitational field and being in free fall produce the exact same physical sensation, then maybe gravity and acceleration are not two different things. Maybe they are the same phenomenon, viewed from different perspectives. This became known as the equivalence principle, and it is the seed from which all of general relativity grew. Here is where the story usually gets rushed in most science content, and where we are going to slow down, because this is the actual mechanism, and it deserves to be understood properly rather than gestured at. Einstein spent the better part of a decade, from 1907 to 1915, working out the mathematical consequences of the equivalence principle. He needed a new kind of geometry, one that could describe a universe where space and time were not a fixed, rigid backdrop, but a flexible, responsive fabric. He found what he needed in the work of the 19th century mathematician Bernhard Riemann, whose non-Euclidean geometry described curved surfaces mathematically, decades before anyone imagined it might describe the actual universe. Einstein, with crucial mathematical assistance from his friend and collaborator Marcel Grossmann, adapted Riemannian geometry into a four-dimensional framework combining 3 dimensions of space with 1 dimension of time. This combined structure is what we now call spacetime. And here is the reversal that this entire video has been building toward. In Einstein's theory, mass does not reach out and pull on other masses through empty space, the way Newton's law implied. Instead, mass and energy tell spacetime how to curve. Objects then move through that curved spacetime, following the straightest possible path available to them, called a geodesic. When the Earth orbits the Sun, it is not being yanked by an invisible gravitational rope. It is simply following the straightest possible path through a region of spacetime that the Sun's enormous mass has warped. The way a bowling ball placed on a stretched rubber sheet creates a dip that changes the path of a marble rolling nearby. The marble is not being pulled by the bowling ball. It is following the curve created by the bowling ball's weight. This is, admittedly, a simplified analogy, and physicists, including Einstein himself, worried it could mislead people into thinking gravity requires an external force to create the curve, when in fact the curvature is happening in 4-dimensional spacetime itself, not in some third dimension we can visualize from outside. But the core insight survives the simplification. Mass does not create a pulling force. Mass creates curvature, and that curvature is what we experience as gravity. Let's pause here and let this sink in, because this is not a minor technical distinction. It is a complete reversal of the causal story. In the Newtonian picture, gravity is a force, transmitted instantly, acting between 2 masses regardless of the distance between them. In Einstein's picture, gravity is not a force at all in the traditional sense. It is geometry. It is the shape of the universe responding to the presence of mass and energy, and objects moving in straight lines through a universe that is no longer flat. Einstein published the complete field equations of general relativity in November 1915, presenting them to the Prussian Academy of Sciences in Berlin. These equations, compact enough to fit on a single line yet notoriously difficult to solve, describe precisely how the presence of mass and energy determines the curvature of spacetime, and how that curvature in turn determines how mass and energy move. It is a feedback loop between matter and geometry, and it replaced the idea of gravity as a distant pull with gravity as a local response to the shape of space itself. Now, a theory this radical needed proof, and this is where the investigative backbone of this story gets genuinely dramatic. Einstein's equations made a very specific, testable prediction that differed from Newton's theory. If mass curves spacetime, then light itself, even though it has no mass, should have its path bent as it travels through that curved space, because light too must follow the geodesics of spacetime. Newton's theory predicted some bending of light due to gravity, but Einstein's theory predicted exactly twice as much bending. This was a number you could actually measure if you had the right conditions. The problem was that testing this required observing starlight passing extremely close to the Sun, something normally impossible because the Sun's brightness overwhelms the light of any star near it. The solution was a total solar eclipse. In 1919, the British astronomer Arthur Eddington organized 2 expeditions, one to the island of Príncipe off the coast of West Africa, and another to Sobral in Brazil, to photograph a solar eclipse and measure the exact positions of stars whose light passed close to the Sun's edge during totality. This was an enormous undertaking. World War I had only just ended months earlier. Eddington himself was a Quaker and a conscientious objector who had faced pressure regarding military conscription, and some historians have noted that his eagerness to test a German scientist's theory carried a quiet, principled defiance of the nationalist hostilities of the era. He sailed to a remote island with fragile photographic equipment, uncertain weather, and a theory that, if wrong, would have made the entire expedition a very public failure. On September the 22nd, 1919, Frank Watson Dyson, the Astronomer Royal, along with Eddington, presented the results to a joint meeting of the Royal Society and the Royal Astronomical Society in London. The measurements matched Einstein's prediction, not Newton's. Light bent around the Sun by almost exactly the amount general relativity predicted. The physicist and philosopher Alfred North Whitehead, who was present at the meeting, later described the atmosphere as similar to a Greek drama, with the announcement of a fundamental change in humanity's understanding of the cosmos delivered live to a room full of scientists. The next day, newspapers around the world ran headlines proclaiming a revolution in science. Einstein, virtually overnight, became the most famous scientist alive, and the idea that mass curves spacetime rather than exerting a direct pull moved from a strange mathematical hypothesis to an experimentally verified description of reality. But the story does not end with one eclipse in 1919. Over the following century, general relativity has been tested again and again in increasingly precise and increasingly strange ways, and it has passed every single time. Mercury's orbit around the Sun had a small, persistent anomaly that Newtonian physics could never fully explain. A slow shift in the point of its orbit closest to the Sun, known as perihelion precession. Astronomers had tried for decades to explain it by hypothesizing an undiscovered planet, sometimes called Vulcan, orbiting even closer to the Sun. No such planet was ever found. Einstein's equations, without any additional assumptions, predicted the exact residual shift in Mercury's orbit that observations had already measured. This was, for Einstein himself, one of the most emotionally significant moments of his career. He reportedly said the discovery gave him heart palpitations because a puzzle astronomers had puzzled over for half a century simply fell out of his equations naturally. Then there is time itself, which general relativity insists is not a fixed universal clock ticking the same everywhere, but something that flows differently depending on how deep you are inside a gravitational well. Clocks closer to a massive object, where spacetime curvature is stronger, run slower relative to clocks farther away. This is not speculative, it is something engineers have to correct for every single day, because the global positioning system relies on atomic clocks in satellites orbiting the Earth. And those satellites experience weaker gravity than we do on the surface, causing their onboard clocks to run faster than clocks on the ground by about 38 microseconds per day. This sounds tiny, but without correcting for it using Einstein's equations, GPS location errors would accumulate by several kilometers within a single day, rendering the entire system useless. Every time your phone locates you correctly, it is quietly relying on the fact that mass curves space-time and that curvature affects the passage of time itself. And then, in 2015, exactly 1 century after Einstein first presented general relativity, came perhaps the most spectacular confirmation of all. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected a ripple in the fabric of space-time itself, produced by 2 black holes, each roughly 30 times the mass of our Sun, spiraling into each other and merging over 1 billion years ago. The collision was so violent that it briefly radiated more power in gravitational waves than all the stars in the observable universe combined in visible light. And yet, by the time that ripple reached Earth, it stretched and compressed the arms of LIGO's detectors by a distance thousands of times smaller than the width of a proton. Scientists Rainer Weiss, Barry Barish and Kip Thorne received the Nobel Prize in Physics in 2017 for this detection, decades after the theoretical groundwork and instrument design first began. This was direct physical evidence that spacetime is not a passive state on which matter performs. It is a dynamic, flexible medium that can literally ripple like the surface of a pond in response to the movement of extremely massive objects. Mass does not just create a static curve. Moving mass sends waves through the geometry of the universe itself, waves we can now directly detect on Earth. So by this point in our investigation, the evidence is overwhelming, and it is not remotely in dispute among physicists. Mass does not pull on other mass through some invisible force reaching across empty space, the way the Newtonian picture in our heads still often imagines it. Mass curves the four-dimensional fabric of spacetime, and objects, including light itself, simply follow the straightest available path through that curvature. This is what falling actually is. This is what an orbit actually is. This is what your own weight actually is right now as you sit and listen to this. You are not being held down by a force reaching up from the Earth's core. You are resisting the tendency to follow a geodesic path that would otherwise carry you straight through the floor and toward the center of the planet. And the floor is providing the resistance you feel as weight. Now here is where we deliver on the second half of this video's promise, because the title made a very specific claim. Einstein was only half right. And this is not a dramatic exaggeration for the sake of clickable phrasing. This is an acknowledgement that serious physicists make openly, and it deserves the same careful, evidence-based treatment we have given everything else in this investigation. This is the reality check. General relativity is, without question, one of the most successful and rigorously tested theories in the history of science. But it has two enormous, well-documented problems, and both of them point towards something being fundamentally incomplete about the picture of gravity as pure geometry. The first problem is what happens inside a black hole, or at the very beginning of the universe. Einstein's equations, when applied to these extreme conditions, do not produce a strange but sensible answer. They produce infinity. At the center of a black hole, according to general relativity's own mathematics, spacetime curvature becomes infinitely large. Density becomes infinite, and the equations simply break down and stop giving meaningful predictions. Physicists call this a singularity, and virtually all serious researchers, including Stephen Hawking and Roger Penrose, whose singularity theorems proved in the 1960s that such breakdowns are an unavoidable mathematical consequence of general relativity under very general conditions, treat this not as evidence that black holes literally contain infinite density, but as a signal that general relativity itself stops being an accurate description of reality at that scale. Penrose received the Nobel Prize in Physics in 2020 specifically for this work, demonstrating mathematically that general relativity predicts its own downfall in sufficiently extreme conditions. The second problem is even more fundamental, and it is the single biggest unresolved question in all of theoretical physics. General relativity describes gravity as smooth, continuous curvature. But every other force in nature, electromagnetism, the strong nuclear force, and the weak nuclear force, is described by quantum mechanics, a framework where energy and interactions come in discrete, granular packets rather than smooth, continuous curves. These two descriptions of reality, general relativity's smooth geometric gravity and quantum mechanics' granular probabilistic forces, have never been successfully merged into one unified theory. Every attempt to simply apply the mathematical tools of quantum mechanics directly to gravity produces nonsensical results, infinite probabilities that cannot be resolved through the techniques that work perfectly well for the other three forces. This is not a minor technical inconvenience. It means that our two most successful theories in the history of physics, the theory that explains the very large and the theory that explains the very small, are fundamentally incompatible with each other, and nobody yet knows exactly why or exactly how to fix it. This is precisely why saying Einstein was only half right is not sensationalism. It is an accurate summary of where mainstream physics actually stands today. Einstein correctly identified that gravity is geometry, not a Newtonian pulling force, and that insight has been confirmed by over a century of increasingly precise experiments. But general relativity, as a purely classical continuous theory of geometry, cannot be the final complete story, because it fails catastrophically at the smallest scales and the most extreme densities, exactly where a truly complete theory of gravity would need to work perfectly. Physicists have spent decades searching for what comes next. String theory proposes that both matter and gravity emerge from tiny vibrating strands of energy operating in extra hidden dimensions. Loop quantum gravity proposes that space-time itself is not smooth at all, but made of discrete, indivisible loops at the smallest possible scale. A scale so small, roughly the Planck length of about 166 tillionths of a trillionth of a meter, that it is currently far beyond what any instrument on Earth could directly probe. And in 2010, the physicist Erik Verlinde, building on ideas about black hole thermodynamics developed by Jacob Bekenstein and Stephen Hawking in the 1970s, proposed an even stranger possibility, published in his paper titled On the Origin of Gravity and the Laws of Newton. Verlinde argued that gravity might not be a fundamental force or even fundamental geometry at all, but an emergent phenomenon, arising statistically from the entropy and information encoded on hidden surfaces in the universe, in the same way that temperature emerges from the statistical motion of countless individual molecules, without any single molecule itself possessing a temperature. Under this view, mass does not create gravity directly at all. Mass influences information, and gravity emerges as a large-scale, almost thermodynamic side effect of that information reorganizing itself. None of these competing ideas, string theory, loop quantum gravity, or emergent entropic gravity, have been experimentally confirmed the way general relativity has. This is important to say plainly and honestly, because a channel built on evidence-based reframing does not get to quietly skip over the uncertainty just because it makes for a less tidy ending. The honest state of physics today is this. We know with overwhelming experimental confidence that mass curves spacetime, and that this curvature, not a Newtonian pulling force, is what produces the phenomenon we call gravity. But we do not yet know what is truly happening underneath that curvature, at the deepest, smallest, most fundamental level of reality, in the way that would finally reconcile gravity with quantum mechanics. That gap is not a failure of Einstein. It is the next great unsolved mystery he handed to every physicist who came after him. It's worth sitting for a moment with the human cost behind all of this, because these are not just equations on a chalkboard. Einstein worked on the mathematics of general relativity for nearly a decade, and in the final months before publishing the complete field equations in November 1915, he was in a genuine race against the brilliant mathematician David Hilbert, who was independently approaching a similar set of equations through pure mathematics. Historians have spent decades poring over letters and manuscripts trying to determine exactly who deserves priority for the final form of the equations, a debate that, in some corners of the physics history community, continues even now. Einstein himself described this period as one of the most exhausting and emotionally turbulent of his life, at one point writing to a friend that he was so absorbed in the problem that he had neglected nearly everything else, including his own health and his strained personal relationships, which were unraveling around the same time as his marriage to Mileva Maric was ending. Eddington risked his scientific reputation and endured genuinely difficult travel and equipment conditions on a remote volcanic island to test a foreign rival's theory in the aftermath of a devastating war, at a time when nationalist tension between British and German scientific communities ran extremely high. And the LIGO detection in 2015 was the product of a scientific collaboration that had been building, refining, and failing to detect anything at all for over 40 years before that first successful signal arrived, with some of the founding scientists dedicating their entire careers to an instrument that, for decades, had detected absolutely nothing. This is the quieter, more human layer beneath every equation we have discussed today. Behind the elegant idea that mass curves spacetime rather than pulling on it directly are real people who gambled careers, reputations, and years of their lives on the possibility that our intuitive, everyday sense of gravity as a simple pull was simply wrong, and that the truth was something far stranger and far more beautiful hiding underneath it. There is one more piece of this puzzle worth understanding, because it explains why physicists have not simply shrugged off the incompatibility between general relativity and quantum mechanics as someone else's problem to solve later. Every few years, new experiments are specifically designed to probe the boundary where these two frameworks should, in theory, start to overlap. The Event Horizon Telescope collaboration, a global network of radio observatories effectively turning the entire planet into one enormous telescope, produced the first ever direct image of a black hole shadow in 2019, capturing the supermassive black hole at the center of the galaxy Messier 87, and followed in 2022 with an image of Sagittarius A star, the black hole at the center of our own Milky Way. Both images matched the predictions of general relativity's geometry with remarkable precision, right up to the very edge of the event horizon itself, the boundary beyond which our current physics simply stops being able to say anything reliable at all. Every one of these results narrows the gap slightly, ruling out competing modifications to gravity one at a time, without yet delivering the single unifying answer physicists are searching for. There is also a quieter, more philosophical layer to this story that rarely gets discussed outside of physics departments, and it concerns what curvature actually means. When we say mass curves spacetime, we are not describing spacetime bending into some third hidden dimension the way a bowling ball dents a rubber sheet by sinking downward into empty air beneath it. That analogy, useful as it is for building intuition, secretly smuggles in an extra dimension for the sheet to sink into, a dimension that does not actually exist in Einstein's mathematics. The real curvature described by general relativity is intrinsic, meaning it can be fully defined and measured entirely from within spacetime itself, without any need for an outside space to curve into. This is closer to the way the surface of the Earth is curved. You do not need to leave the Earth and view it from space to prove it is curved. You can prove it by noticing that the sum of the angles of a large enough triangle drawn on its surface exceeds 180 degrees, a purely internal measurement. Spacetime curvature works the same way, detectable entirely through measurements taken from inside it, which is part of why it took a mathematician as sophisticated as Riemann to even develop the tools capable of describing it decades before Einstein needed them. So where does this leave us today, standing at the edge of what we actually know? Mass does not create gravity in the way most of us were taught to picture it, as an invisible hand reaching across space. Mass tells the geometry of the universe how to bend, and everything else, falling apples, orbiting planets, the weight pressing you into your chair right now, is simply the natural consequence of objects following the straightest paths available to them, through a universe that is no longer flat. This has been confirmed by starlight bent around the Sun in 1919, by the otherwise unexplainable orbit of Mercury, by the atomic clocks quietly correcting themselves in the satellites above your head every single day, and by ripples in spacetime itself detected on Earth in 2015, a full century after Einstein first proposed the strange idea that made all of it possible. And yet, at the very extremes, inside black holes and at the birth of the universe itself, this beautiful geometric picture breaks down completely, refusing to merge with the quantum rules that govern everything else in nature. Einstein handed us a universe made of curved space and flowing time, more accurate and far stranger than anything Newton imagined, and then, in doing so, honestly revealed the next mystery still waiting to be solved. Somewhere in the gap between smooth geometry and quantum granularity lies the true, complete answer to what gravity actually is, and as of today, no one on Earth has found it yet. If this kind of evidence-based reframing of the ideas you thought you already understood is the sort of investigation you want more of, there is a full case file archive here covering everything from the physics of stopped light to the true nature of stardust. Each one built the same way this one was, from verified sources, named scientists, and curiosity gaps that actually get resolved by the end. Subscribe if you want the next file the moment it's opened.